Today, we're taking a microscopic, high-speed journey to see exactly how the internet works. We're going to track one single data packet from your smartphone all the way across the globe to Google servers and back again. Let's get into it. So, what actually happens the exact second you type google.com and hit enter? I want you to imagine zooming right in on your phone, the millisecond your finger taps that screen. Immediately, a jaw-dropping sequence of magical engineering kicks into high gear. Your browser creates a request asking Google's server to send over the homepage. But to understand how that request actually goes anywhere, we kind of have to look at the bigger picture first.
Section 1. The invisible global network.
You know, we always talk about connecting to the internet, but the crucial point here is that the internet isn't a single giant machine. It's definitely not a magical cloud floating in the sky. It's actually a physical network of networks. Your home Wi-Fi is one network. Your mobile carrier is another. Universities, governments, big companies, they all have their own. The internet simply connects all of these independent networks together using standardized communication rules, which we call protocols. It's kind of like a massive global road system connecting every city in the world. But instead of carrying cars, it carries data.
Section 2. Finding the destination.
Before our data packet can even leave the driveway of your phone, it needs an exact set of coordinates to know where it's going. And here's the catch. Computers absolutely do not understand a name like google.com. They only communicate using numbers, specifically IP addresses. Enter DNS, or the domain name system. It essentially acts as the internet's phone book. Your device has to convert google.com into a numerical IP address, something like 142.250.whatever. So your computer rapidly checks its own browser cache, the operating system cache, and your router's cache. If it still can't find it, the request travels to your internet service provider to get those exact numerical coordinates. All right, once we finally have the destination IP address, the real magic begins. Let's shrink down to a microscopic level here. The internet doesn't just send your request as one giant file. Instead, it divides your information into thousands of tiny little pieces called data packets. And every single one of these packets carries a digital shipping label. That label has the source address, the destination address, a specific packet number, error checking info, and of course, the actual payload, which is the data itself. Think of it like trying to mail a heavy 500-page book. Instead of mailing one massive package, imagine you put each page into 500 separate, numbered envelopes and mail them independently. Even if these tiny digital envelopes take completely different routes through the mail system or show up totally out of order, it doesn't matter. The destination server uses those packet numbers to seamlessly rebuild the original book the second it arrives. Leaving your phone, our microscopic packet's very first hop is your home router. Your router is essentially the local traffic controller deciding where every single packet should go next. But it also does something incredibly vital called network address translation, or NAT for short. NAT allows your phone, your laptop, and your smart TV to all share one single public IP address. Frankly, without NAT, the internet would have completely run out of addresses years ago. So your router takes your packet and forwards it to your internet service provider. Companies like Comcast, Airtel, or Geo, who use their vast infrastructure to figure out the best route forward. Section 3. The ocean crossing journey. Now, this might shock you. When you send data across the globe, over 95% of that internet traffic doesn't go to space via satellites. No way. The vast majority of our data actually travels through submarine fiber optic cables, stretching thousands of kilometers right across the literal ocean floor. Imagine our microscopic data packet transforming into a pulse of pure laser light. Inside these undersea fiber optic cables, lasers are firing light pulses that represent binary data. And because it's light, it travels incredibly fast, allowing our information to rocket across continents and ocean floors in just milliseconds. All while routing protocols are continuously calculating the absolute fastest path, instantly shifting traffic if one route fails. It is wild. Along this high-speed journey, our pulse of light zips through Internet Exchange Points, or IXPs. You can think of these as massive international highway intersections. They're physical locations where different internet service providers connect their networks to exchange traffic directly with one another. Without IXPs, our packet would have to take these ridiculously long, highly inefficient routes. These intersections dramatically improve global internet speed, and they significantly slash costs.
Section 4. Inside the data center.
We made it! After navigating local routers, ISP networks, and ocean-spanning fiber optic cables, our tiny data packet finally hits its physical destination on the other side of the world. Zooming into one of Google's enormous data centers, it is an absolute hive of activity with hundreds of thousands of servers. To manage this total chaos, our packet first passes through a load balancer. It acts like a highly efficient traffic cop, perfectly distributing all incoming global traffic across the servers so that no single machine ever gets overloaded or causes a bottleneck. Once our request lands on an available server, that machine immediately springs into action to build the Google homepage. It gathers the HTML for the structure, the CSS for the visual styling, the JavaScript for interactivity, and all the images, videos, and fonts. It grabs all these totally separate resources and instantly chops them all back up into thousands of return packets, getting them ready for the long journey back to your screen. Section 5. The encrypted return trip. Okay, so now our newly created response packets have to blast back across the globe to your phone, but this time they need armor. Modern websites use HTTPS, so before these response packets leave the server, your browser and the Google server perform a lightning-fast process called a TLS handshake. This instantly creates a secure, encrypted communication vault. Because of this encryption, even if a bad actor manages to intercept our microscopic packets at the bottom of the ocean, they literally cannot read the contents without the specific encryption keys. This is the invisible shield protecting your passwords and banking info every single day. And to make this return trip even faster, large companies utilize content delivery networks, or CDNs. A CDN stores copies of heavy website elements in servers all around the world. So say you're browsing from India. The core text might come from a central server, but heavy items like images or videos, they might not cross the ocean at all. Instead, they just pop over from a CDN server located maybe a few miles from your house. This completely slashes the geographic distance and drastically cuts down your loading times. But of course, the internet is only as fast as its slowest link, right? Sometimes you get a weak Wi-Fi signal or network congestion, and a packet gets lost or corrupted along the way. Well, the internet has a built-in safety net for that called the Transmission Control Protocol, or TCP. TCP meticulously checks the incoming packets, spots any missing envelopes, and re-requests just those specific missing pieces from the server. So you don't have to download the entire web page all over again. Section 6. Rebuilding the magic. Our packets have successfully navigated local routers, massive ISP networks, literal oceans, high-speed intersections, load balancers, and encryption protocols, and they finally arrive safely right back at the antenna of your phone. In a fraction of a second, your browser takes these thousands of incoming packets and gets straight to work. First, it uses the HTML to build the structural skeleton of the page. Next, it applies the CSS to paint the colors and visuals. And finally, it layers on the JavaScript to add all the buttons and interactivity. It combines all these incoming pieces perfectly to paint the familiar Google homepage right onto your screen. Let's recap this entire cinematic journey on a timeline, just to put this into perspective. At exactly 0 milliseconds, you hit enter and your device creates the request. By 10 milliseconds, the DNS has found the IP address. By 30 milliseconds, your laser-light packets are already crossing the ocean floor. At 50 milliseconds, Google's server is building the encrypted response, and by 80 milliseconds, your browser renders the page. This entire mind-bending global trip happens in just a few dozen milliseconds. Honestly, it is one of humanity's greatest engineering achievements. It happens flawlessly, billions of times a day without any of us ever noticing. Which leaves us with a pretty fascinating thought to ponder. If we can engineer a system that seamlessly blasts microscopic packets of data across the ocean floor and back in the literal blink of an eye, what other incredible, invisible engineering miracles are happening every single time you tap your phone? Thanks for joining me on this explainer, and keep wondering about the invisible world around you.